In this video, we're going to look at the connection between solving systems of equations and matrices. So here's a very simple simultaneous equations. Now, how would you solve this? If I was asked to solve this, I would probably double this second line, 2x plus 8y equals 14, and I'd probably do this line minus this line. The x's cancel, 8y minus y is 9y, 14 minus 5 is 9. That gets me my y value. Then I can just find x. So 2x minus 1 equals 5, and x is 3. You didn't do this course to learn how to solve simultaneous equations, but here is a clever but weirdly inefficient way of solving these. Take these two equations and convert them into the following matrix. It's really a matrix equation because look, this is saying exactly the same thing. This is saying 2x minus y equals 5 and x plus 4y equals 7. How could we solve this? Well, we could take the inverse of this and left multiply both sides by that. So 2 minus 1, 1, 4 to the minus 1 and apply that to 5, 7. Now, can we do that? Sure, we can. So find the determinant. That's 8 minus 1, so that's 9. So 1 over the determinant. Then swap these round for 2, make the other 2 negative, and we're there. Now, I told you this is a weirdly inefficient way to do it, but it's just showing the principle at play. What do we get? That's 20 plus 7 is 27. And minus 5 plus 14 is 9. And lo and behold, xy is 3, 1. And yeah, that works. So we could, if we wanted, solve systems of equations using matrices, and it's kind of clever to do so. In the 3 by 3 case, well, we don't really want to find inverses of 3 by 3. We can do it, but it's hard work. So here's our setup. We've got the matrix 1, 1, 1, 2 minus 1, 1, minus 1, 3, minus 2, applied to x, y, z equals 2, 7, minus 13. So I'm going to show you a way of solving this without finding the inverse of this matrix. Now the process is we're going to use something called Gaussian elimination, named after Gauss, the mathematician. And we're going to use Gaussian elimination to get it into what's called row echelon form. Okay, what an awful lot of jargon, but actually the process is very, very simple. We're going to start with what's called an augmented matrix. Okay, even more jargon. An augmented matrix is simply where we take the matrix corresponding to the left-hand side, which is exactly what I've already done up there, but don't close the bracket on the right just yet. Then we put a little dotted line down there and we put the right-hand side. So we're just leaving off all of the letters. Now, here's the process. We are aiming for this left-hand side to be in row echelon form. Row echelon form is a matrix where the bottom row is zeros here and here, and then something there. The row above must have a 0 here and could have something there, and the top row can have whatever we want, D, E, F. If it was a bigger matrix, it'd be the same thing. It's just you can only have zeros and then one term, and then the row above should be zeros and 2 terms, and then 0 and 3, and so on. Now, why is it called echelon? Well, echelon means rung in French, like the rung of a ladder. We also talk about different echelons of society, don't we? These are like rungs, basically, and it's like a little step here. So these are the kind of the echelons there. So we're aiming for this form, and we're aiming for this form because it's going to be easy to solve when it's in that form. Now, how do we get it into that form? Well, that's what we use Gaussian elimination for. This is row 1, this is row 2, this is row 3. My first aim is to get zeros below the leading term here. So I want 0 here and I want 0 here. And I do this by combining any of the rows that I've got with any others. Here's what I mean. I could convert this to a 0 by taking all of this row and adding on all of this row. So I'm going to replace row 3. So row 3 is going to become my old row 3 plus my old row 1. Because when I add these two together, that's going to give me that 0 there. Now, you can do any sort of combination you like as long as row 3 doesn't disappear. Right? If you don't use, if I just replaced row 3 with sort of row 2 minus 2 times row 1, well, row 3, the information from row 3 is gone. But as long as I never totally get rid of it, the information is preserved. So doing this is going to get rid of that minus 1 there to give me the 0 that I need here. And then I also want to make this term 0 as well. And I can do that by saying row 2 is going to become, well, look, if I take my old row 2 and I subtract 2 times my old row 1, then it'll be 2 minus 1 there. So here are the operations I'm going to do, and what does this do to my augmented matrix? Well, the first row is unchanged. 1, 1, 1, 2. Okay, row 2 becomes old row 2 minus 2 times row 1. So 2 minus 2 is 0, that's what I wanted. And then minus 1 minus 2 of these, that's minus 3. Then 1 minus 2 of these minus 1, and 7 minus 2 of these gets me 3. Now my new row 3 is just my old row 3 plus my old row 1. Minus 1 plus 1 is 0, that's what I wanted. 3 plus 1 is 4. And minus 2 plus 1 is minus 1. Minus 13 plus 2 is minus 11. Okay, row 2 is done. I've got the 0 that I wanted there, but row 3 is not done. Now, I'm going to use row 2 combined with row 3 to reduce this one down to 0. Now, I'm not going to use row 1 because row 1 has a 1 there, which could clog things up here. But if I use row 2, which has a 0 here, I won't interfere with that. So how do I get a 0 here? Well, I could say I'm going to add 4/3 of this. That's going to get messy. But what I am going to say is that my new row 3 is going to be, well, how about 3 of these plus 4 of these? That will get me to 0. So 3 row 3s plus 4 row 2s. So let's see what that gets me. First row is unchanged. 1, 1, 1. And a 2 here. Next row is unchanged, 0, minus 3, minus 1, 3. Right, R3 is 3R3 plus 4R2. So 0 here, then it's 3 of these plus 4 of these, which is 0. That was the whole point. Then 3 of these, minus 3, plus 4 of these, minus 4. So minus 3 plus minus 4 is minus 7. 3 of these, minus 33, plus 4 of these, 12, minus 33, plus 12 is minus 21. We now have used Gaussian elimination, that's all of this row business, and we've turned it into row echelon form. There's our little staircase of zeros down there. And now it's totally trivial to solve, because look what row 3 is saying. It's saying 0x plus 0y minus 7z equals minus 21. So z is 3. And now we can use that z value here to solve the second row. 0x minus 3y minus z, which I know is 3. So minus 3y is 6, and y is minus 2. Now I'll use those in the top row. X plus y plus z equals 2. I think we get x equals 1. And there's my solution to that system of simultaneous equations. So, yes, there's a lot of jargon. We're using Gaussian elimination to reduce my augmented matrix down to row echelon form, but in practice, it's quite easy. Ready to have a go with one yourself? Here you go. So pause the video and try to use Gaussian elimination to reduce your augmented matrix to row echelon form and then solve. Okay, so let's start with the augmented matrix. Step 1, let's get zeros in everything below the 1 here. So row 2 could just be our old row 2 minus 2 lots of our old row 1. That will get rid of that. And our new, and you know what, I really should actually be using an arrow there rather than equals, because I'm saying it's what it goes to, not what it is. And my new row 3 is going to go to, let's just take my old row 3 minus 3 lots of my old row 1. So what do we get? First row stays the same. Row 2, so it's this minus 2 of these is 0. Minus 1 minus 2 times 2 is minus 5. 1 minus 6 is minus 5. And 5 minus 10 is minus 5. This row is going to be my old row 3 minus 3 of these. So we get 0 there as required. 1 minus 3 of these, that's 1 minus 6 is minus 5. And then minus 2 minus 3 of these, minus 9, that's minus 11. And then 16 minus 15 is 1. Okay, this is looking good. I'm now going to use these two. So I think I can just do that my new row 3 is going to go to my old row 3 minus my old row 2, because minus 5 minus minus 5 gets me the 0 I want. So first row remains unchanged, second row remains unchanged, third row becomes minus 5 minus minus 5 is 0, minus 11 minus minus 5 is minus 6, and 1 minus minus 5 is 6. I know all of these lines you could obviously divide through this by 5, but we don't really need to. By the way, you can. If it's ever useful, what we could have done is said, by the way, I'm actually just going to replace row 2 with a fifth of the old row 2. But I often don't bother with that. Right, it's in row echelon form. I've reduced my augmented matrix using Gaussian elimination down to row echelon form. Solving the bottom line, we have minus 6z equals 6. So z is minus 1. Row 2, we have minus 5y minus 5 times z, so that's plus 5, equals minus 5, giving me minus 5y equals minus 10, and y is 2. And then the first row has x plus 2y plus 3z equals 5. So that gives me x equals 4. Now there's my solution, which I could write as a vector if I wanted, 4, 2, minus 1. And that's the solution to this set of simultaneous equations. All right, so that's all of the technique. In the next video, we're going to explore geometric interpretations of this method, which is rather fun. So I'll see you there for that.